this is 127, and I don't think there is editions of the Shellcoder's Handbook. If you're talking about this class, I think there hasn't been a new version of this in years. Is there a new edition of the Shellcoder's Handbook? This is important. Let me see. All right, let's see. Looks like my Amazon link is not working. I'm seeing a newer one from 2011, but I can't get hold of it. Well, this is the one I used, this ASIN number. And for some reason, here we are. Maybe this is the one I used, which is the only one I've read. The second edition is the one I used, the only one I know about. And it's quite a few years old, I know that. But so as far as I know, this is the one to use, and it's easily available all over the place. I don't know about any other edition, so if you have some other edition, it might be all right, I'm not sure. That's the only one I've ever seen, and it's considered a standard in the business. Everybody has read this book, everybody refers to it. Parts of it are old, but I've written some content to supplement it. So anyway, let me talk about this class in general. The point of this class is exploit development, and exploit development is improving attacks to make them more powerful, finding vulnerabilities and developing code that will attack servers and take them over. And that is a skill which has become important in security, of course, and it all started with Aleph Null, who was published in Frac magazine, How to Do Buffer Overflows, about 25 years ago. And that exposed a technique that was only known in secret to the black hat hackers, to the whole world, and that started people learning how to do exploit development, and that's what we're going to cover here, how to develop attacks. And the point of this, of course, is that you learn how to protect machines, you learn how to write better software, how to write better operating systems, if you understand how the attacks work. So you can get a free copy of the textbook online here from the City College bookstore, has some kind of, or library has some kind of deal with Safari. So if you have a City College email address, you'll be able to get a free online copy there. You can also get the book other places. And so we're going to talk about how to exploit Windows and Linux in this course. All right, there's a Canvas shell for this course at the usual one. If you start at ccsf.edu and go up here and click Canvas and log in, you will see the courses you're enrolled in, and one of them is this course. And in there you'll find the quizzes and a place to turn in your homework. But most of the content for the course is on my webpage, which is samsclass.info. If you go to samsclass.info, then the courses are here towards the top, and there it is, 127. That takes you to the page for this course, which has lectures and videos will be appearing on here, and there's a link to the projects that are on a separate page where you can do these hands-on projects, which are the most important part of the course. There are quizzes in Canvas, and you read through the textbook and learn the concepts, and you practice it with these hands-on projects. So there's various ways to, various contributors to the grade. The grade comes from just your total number of points, and the points come from projects, hands-on projects, quizzes, and I think that's it on the final exam. I don't think there's discussions in this course. So the point is there's a certain number of points, and 90% is an A, 80% is a B, and so on. And I'll publish the chart of how many points it takes to get various grades at midterms and at finals. Nobody should be surprised what grade you're getting. And there's a lot of extra credit projects. So you can make up for anything you do badly on a quiz, you can make up for it by doing more projects. All right. Attendance is not required. You do not need to come physically. You don't even need to turn in online. All you have to do is learn the stuff somehow. You do not need to come physically. You can connect to the Twitch channel if you like many people are doing right now, and just connect to hear the lecture live. You can also ignore that and view a YouTube video later. The YouTube videos will be on this 127 page. I post them every night after class. So here's the schedule, and later tonight after class, I will put some videos here. You'll just be able to look at videos of the lecture if you want to. All right. Are there any questions about anything? Had one person that wanted to add, just make an add request in this computer system, the City College system, and I will approve them. Let's see what's happening here. Is the last day to add this course early February? I think that's true. I know you have several weeks. Let me check the schedule. I've got a link to it here. Okay, spring 2023. Last day to add is Friday, the 3rd of February. Yeah, so you have until then, about 2 weeks. Good? All right. And, all right, so let me move on to the first chapter then, I think. We'll get back to this stuff. The first chapter is here. Oops, not there, but here. All right. There it is. Okay. And be aware, by the way, the book is kind of dense and hard to read, and I'm not covering it all for that reason. Oh, let me see if I can do something about these fonts, just to get rid of this message. Oh, no. I wanted to make it normal Arial, regular, there we go. Okay, now maybe it will stop bugging me. All right, so here's the basic concepts. You do need to learn some assembly language and how to handle some binary code in this class. That students often find this difficult. It's not that hard, but you do have to get used to it. You're going to learn how computers really work at the binary level and how memory is really used at the binary level, so you can perform memory exploit, memory corruption attacks. And yes, someone asked about non-CCSF students. You can completely take this course if you're a non-CCSF student, and you'll find, I'll add the link here to the other Canvas account, so you can take the quizzes and such. You won't get college credit, but you can do everything and get a grade. So I'll have a link, I'll put it here later. I haven't put it up yet, but I do have a separate Canvas available to everybody for the non-CCSF students. Good? All right, so a vulnerability is a flaw in a system that lets somebody do something they should not be allowed to do, like execute code on a server, denial of service, elevate privileges, and the main vulnerability you want is remote code execution. If you gain the ability to execute arbitrary commands on a server, then you can do anything. So that's generally considered what you really want is an exploit that gives you remote code execution. An exploit is some way, it's the verb is to use the vulnerability, the noun is the code that does the exploit, and that's also called a proof of concept. In the criminal world, they make malware and sell it, but in the legal world, you make proof of concept code to demonstrate the vulnerability, and then there's a huge ethical debate in the field about whether you should publicly distribute proof of concept code or whether you should keep it secret until the thing is patched. The standard in the industry is to wait something like 30 or 90 days. When you find something, you notify the company, you wait something like 30 or 90 days before you go public. Some people wait much longer, like years or forever. Some people just dump everything publicly without telling the company at all. And that is, according to my lawyer, that is legal in America. Because in America, you don't have complete free speech. You are not allowed to say wholly malicious things, but you can argue that exposing a vulnerability helps the customers know. And so that speech that has a good side and a bad side. Anyway, there's arguments about this, but if you want to be respected as an ethical researcher, it's traditional to wait 30 or 90 days after telling the company before you dump it publicly. That's what Google does. And Google finds a lot of vulnerabilities, and they are extremely ruthless about the 90-day deadline. They found a serious vulnerability in Windows a couple of years ago, and Microsoft asked them to delay the public disclosure for 3 days to hit Patch Tuesday, and they refused. So they're not kidding. Anyway, so you find these things. An exploit that has not been publicly disclosed is a 0 day, which you start counting days from the day the patch came out. So a 1 day vulnerability is 1 day after the patch came out, and a 0 days one where the exploit is not known, so nobody can defend themselves. You can't update your software, you can't put a rule in the antivirus or the firewall, you don't know what to do because you don't know about that attack. Therefore, they are the most dangerous and most valuable. 0 days that will let you take over, say, an iPhone, sell for more than $1 million. And mostly they sell to the NSA. You can sell them to underworld people, but the military has the most money. So you can go to exploit brokers. There's 4 of them I know in America, and there's probably more by now. And they mostly will sell your stuff, the really good stuff, to the NSA. However, finding a really good 0 day, like a 0 day and an up-to-date iPhone, is very difficult. And I should mention, though, a student that took this course a few years ago that had worked at Google as a software engineer did, in fact, make a new jailbreak for the iPhone, the first new one in 7 years. And I'm certainly only taught him the basics, but once he got the basics, he went to town and made the latest jailbreak. His name is Axiom X, and the jailbreak, I forget the name. But anyway, so So that's pretty cool, but those things are very hard to find. You really have to be an expert. Now, a fuzzer is the normal way you find a vulnerability. A fuzzer just sends deformed data to the server. So you start with network packets and you do things like flip a few bits and just send broken packets to the server until you make it crash. And when you make it crash, then it has failed to process the incoming data correctly, and then you analyze why it crashed to decide if you can improve that. Now, if you have a crash, you've got a denial of service attack. You can now shut off a server, and that's something. But if you can control the data, sometimes you can improve it to where you get remote code execution on the server, which is more valuable. And that's the process called exploit development. You find a vulnerability here, you find a basic exploit, and then you develop the exploit into a more powerful exploit. So mostly we're going to do 32-bit exploits here, although we will do 64-bit Intel too. We're only going to do a little bit of ARM, although ARM is getting more and more important. I'm using an M1 here, so that's an ARM processor, and the M2 is an ARM processor, so we'll do some ARM exploits anyway. But we're starting with the easy system, 32-bit Intel. That's the simplest one to start from, and the others are minor variations on that. So you have to understand how memory is used. So, all right, here's the fundamental reason why all of this works, is that computers are stupid. They do not understand what they're doing. So if you have a series of bytes, the type of data is not labeled anywhere. That could be text, it could be a video, it could be an image, it could be executable instructions, and there's no mark to tell you that. In retrospect, it might have been better if we had something like 10 bits per byte and we had 2 bits that marked whether it's executable or not, but we don't. So your computer can be fooled. So you can take a field that's supposed to take text, like a name or a password, and you can put executable code in there and jump to it and execute it, which sounds insane, but that's the way it is. As far as the computer is concerned, a series of bytes can be used as data or as code, and there's no difference between them intrinsically. That's the fundamental flaw that leads to all these exploits. You trick the computer into taking data and misunderstanding it as code. And that turns out to be far more easy than you might believe it would be. And that's the fundamental way all code execution attacks work. So, when you launch a Windows program, for example, or a Linux program, but in Windows it's this way. When you run a program, it has segments in there. The text section contains program instructions. Here's the data, contains the data variables, and then BSS contains writable stack data. And and we'll play with this a lot more. You'll see this in running code. And so the stack is the most important area where you exploit it. The easiest attack is the stack buffer overflow. That is the classic one that led to almost all the viruses right up through Windows XP. Until Windows Vista, most of them were stack buffer overflows. And some still are, but it's now less of them because Microsoft put more defenses in their operating system. And Linux did too. So this is the point. The purpose of the stack is to handle the flow of modern code. You enter a routine, then you call a subroutine, then that subroutine calls yet another subroutine. So you're running the main program, you're running something like a subroutine, then you're running some other thing like print. So you're in like a dream within a dream. You've partway through this program, remember where you left off, partway through this program, remember where you left off, and now go down here. The stack is where the temporary data is stored to help you resume where you left off. And if you're able to overflow a buffer on the stack, you can confuse the machine, so when it tries to return from the subroutine to the calling routine, it goes to the wrong address and runs code you injected instead of the code the developer expected. That's the fundamental thing you do here. So we'll play with that. Now you can also have heap exploits. The heap is another area like the stack, but it is not structured the way the stack is. The stack has frames, and you create a new frame every time you call a subroutine, and when you return, you pop off a frame, so you pile these things down like a cafeteria trays, and then the last one in is the first one out. It has a logical order for the stack. But the heap has no order. The heap is just a place where you allocate a room for some data, you save some data, then you clear it later. Allocate more room, you put it anywhere you like, and the result is, all right, looks like that's going to work. And anyway, so the heap, you can also heap overflow exploits, and we will do that. But the problem with the heap is not used to return from a subroutine. So there is not normally any address on the heap that controls execution. So heap overflows typically only corrupt data, and they don't make it easy to take over control of the machine, although we'll learn how to do that. It's a little trickier than stack overflows. So here's a picture of the program layout in RAM. You've got kernel space up here. The kernel is reserved only for the operating system. Now I'm seeing a funny message on my screen making me worried that the Twitch stream is not working correctly. Let me see. I'm on the CCSF Wi-Fi. Let me test my network and make sure it's working, because I'm concerned the online people might not be seeing anything.
Turn off the deep freeze.
What's that?
You can turn off the deep freeze.
Oh, well, that's good if you can. You're not supposed to be able to. I mean, if you know how, I'd like to see it. Anyway, so I'm not sure this is still working. Let me check my OBS. No, it says green. Okay, so I think it's working. Can you see me? I'm not seeing any chat messages, and my screen is sort of frozen up here. Let me try refreshing this page for me and see if that does it, because there, okay. Connection has stopped. I lost you at the beginning of the heap slide. Right. Now it's back. Okay, that's what I thought. Something funny happened at the heap slide. So let me go back to that. Good. Now you're, okay. So here, all right. So the heap has, you use the allocate routine to reserve space on the heap, and then when you're done, you free it with free. And it's just pieces. And the problem exploiting the heap is that no part of it is used as a return pointer to control the instruction pointer. So even if you overflow data, you will not hit anything that's used to control the address of the next code to be executed, not directly. You have to use a more indirect process to take over a machine through the heap. You have to use the heap exploit to perform a write operation to write somewhere, which will eventually be used to control execution. And we'll learn how to do that. We write to the global offset table. And so here's program layout in RAM. At the lowest part of memory, you have the kernel space. The kernel is the heart of the operating system that must always be in RAM, and the kernel has complete control of the hardware. You are not going to mess with the kernel much. The kernel contains pretty much only code Microsoft wrote, or the heart of the Linux operating system. Kernel exploits are difficult to make and not that common. Everything you run is in user space. Everything you launch from the start button or the command line is running with user permissions, and it does not have ability to execute all the machine language instructions. It cannot connect to the hardware directly. So if you want to print something on the screen from a program in userland like Microsoft Word, you cannot do it. You are not authorized. The only way Microsoft Word can put something on the screen is by calling a Windows API call to ask Microsoft code in the kernel to please put it on the screen for me. That you have to go through that process. You cannot directly touch any of the hardware from userland. So that's the kernel. Then down here, each program you run will have some sections. It'll have a stack segment, a stack up here, and a memory, and a heap, and other things, like a text segment. It has to have a text segment for instructions. So it's executing instructions, reading data from these various data sections, and the stack is where it's saving information about temporary variables that it uses and making a series of stack frames for all the subroutines you've entered, so you can return from them. And the point is, each program, when you launch it, is assigned certain regions. It can only use a small part of the memory, and it has to stay within. Other programs are using the other pieces of memory. So you have to find the memory you're in. That's the basic structure of the layout, and we'll see it all in great detail with the use debuggers later in the course. So let's try a Kahoot. Let me get those up.
Delay from what you're saying,
yes, yes. There is always a time delay in Twitch. Twitch has a time delay of several seconds, and the people at the other end the Twitch people won't notice it except during these Kahoots. The Kahoots, I made them so they. There. Let me log in here. I made them so that they project to your remote device, so you're not at a disadvantage. Because there is a delay on the Kahoots. Now, let me figure out what this nonsense is. Oh, man. Maybe I need to use a different browser for the Kahoots. Let's try this one. I did it last night without worrying about it. Maybe it was Safari. Just a moment. I got a lot of browsers used for different purposes, and was it this one? Oh, this is the one that failed. Right. I think I got to use Brave. There. Let me try it here. Log in. Yes. There we go. This is going to work now. Okay, let me put this one over here. All right. And what is this garbage? All right, this appears to be it. Library, favorites, all right. See something wrong with my window? No, guess it's as good as it's going to get. Okay, 127. Ah, there we are. 1A. All right, finally getting here. All right. So this is just to keep people from falling asleep, a little online contest. You can earn extra credit if you are one of the top performers here. So go to kahoot.it and put in that number, 861-7278. And the people who are in the top 3 here, they get extra points. They get 3 extra points. It can add up. Okay, good. Okay. Wait a few more seconds. What's that? Kahoot? Yeah, I think it adds the emojis automatically. I think you're right. They're new. They seem to be showing them off. All right, and here's the Twitch stream. I'm just checking. Okay, no comments. Good. All right. All right, people still coming in. I'll give it a few more seconds. Yeah, it ought to let you choose that emoji anyway, or that avatar. That's the word. All right, let's give it a shot. Oh, that's good. Yeah, yeah. Okay. All right, so what's an attack with no defense? Yep, that's a 0 day. All right. It rates you on accuracy and speed. So Woot got the highest score on that one. All right. What's the process of sending random data to a target? All right, that's fuzzing. All right. Okay, what section of memory is LIFO? That's the stack, last in, first out. The last data you put in is the first data that comes out, particularly for the use of the stack for this process of subroutines calling other subroutines. All right, so where are the machine language instructions for a program? And what shepard? In the text section, that's what it's called. It is easy to remember because it's the opposite of what it should be, which, by the way, is true of everything in Microsoft land. Everything is always named the opposite of what it is. The text section is not readable text. It's unreadable machine language code. The text is actually in places like the data section, the readable text. All right. All right, and what section of memory is read-only? Oh, yes. I know what this is referring to, although I didn't mention it in the lecture. We'll talk about it now. All right, it's the text section, and we should talk about this. I forgot to mention it in the lecture. By the way, these Kahoots are extra credit, so if you don't do them or if they seem unfair, that's part of how I cover that. But the point of that is to prevent self-modifying code. I'll talk about it after I record these winners. That winner is Takumi, okay, that looks like a real name. And I know who Root is from before, and Sid, that might be a real name too. All right, so if my grader can figure out who you are, you'll get your points. If you have a different name, then you might want to let me know to make sure you get your points. Anyway, let me talk about that one question. So I used to do this. When I used to write assembly language code for 8-bit processors because I did computing in the 80s when the computers were really, really weak. And you couldn't get much done. You wrote your program directly in assembly code. And I wrote self-modifying code. If you can make code that modifies itself, I used to do it all the time. For example, if I wanted to do a move to a specific address, I had to specifically hard code the address. But if I wanted to do a calculated address, there was no good way to do that. So I would calculate the address and write it directly into the instruction. And you can do that, but that is a terrible practice. People hate it because I didn't think about this. But for one thing, you can't even maintain your code. You can't even print out your code. You can't even read the code. The code changes itself. It's highly insane, unmaintainable, and this is what viruses do. So all modern operating systems do not allow that. It's read or execute, or write or execute. The rule is write or execute in Windows and other operating systems. No memory section is supposed to have both write and execute at the same time. And this will help prevent those kind of exploits we were talking about. Any place you read in data takes the data, but that memory segment is not executable. So it can't accidentally execute the data. And we will overcome that in various ways. But anyway, that's why that question is referring to the text section has to be executable, and therefore it is not writable on any modern system. Although there are exceptions, like the Raspberry Pi 3, everything is read, write, execute enabled in that operating system. It's a defect in the operating system. It's way behind the times in that regard. But most modern operating systems no longer create sections that let you write and execute by default. Although you can make them that way, and you can change permissions to turn on that, so it can be overcome. All right, so let's talk about assembly language, which we're going to use. We're only going to do very simple assembly language in this class. You don't need to learn to write a lot of programs, but we do need to understand how the instructions work and manipulate them a little bit. So assembly language is the human-readable version of machine language. Machine language is the binary code, which is all the hardware understands. All the code it executes is just bits, ones and zeros. But to make it easier for humans, they have turn the instructions into mnemonics and operands that are readable by humans. But it's still not very readable. It's pretty hard to read, but it's easier than reading raw assembly code, the raw binary. So we're going to do 32-bit Intel, the most common type. 64-bit Intel is coming here, and there are many others, like the one I mentioned, ARM. These others are also used, like MIPS is used in some Internet of Things devices. And I know if you take the course here in the CS department, they have an assembly code course that people tell me it's pretty good, but you learn MIPS. But once you learn any one of these assembly codes, it's a small step to learn the others. They all are pretty much the same. Yeah?
The GCC version 12, starting to support MIPS.
CCC version 12? GCC. Oh,
version 12.
GCC? The compiler?
GCC, yeah.
Yeah. Oh, good. I'm glad to hear it. And also, yeah, good. Anyway, so MIPS is coming up, I guess.
China spin out a company to do just MIPS, so
Yeah.
they convince the PCC to add that support.
So are they going to sell like a normal computer with MIPS or anything? Oh, okay, but not yet. But I mean, like I say,
In China, until they can get it here.
yeah, so that's good. Anyway, so for a long time, everything was Intel. And then now we're starting to get ARM, like the Mac M1 and the Mac M2 are ARM. So ARM is coming up. ARM is much faster and uses less power. And I'm not sure what the advantage of MIPS is, but some devices do use MIPS also.
MIPS is no license fee.
No licensing, okay, that's an issue, okay. Anyway, so, all right. So here's an instruction, move ECX 0x42, that's what they look like. The first thing is the mnemonic. The mnemonic is the operation. Move will move data from one location to another. Forming a copy, it's actually a copy operation. Then you have these two arguments. Now, this will move 42 into ECX. The most common format that you see for, I think, Microsoft is the one where you put the from here and the to there. There's another one, just to get you confused, that has them in the opposite order, so the easy way to tell is to look for an immediate constant here. This is a number. It is not an address, and it's not the name of register, so you cannot move anything into that. That must be the thing you're moving into something else. So that this will move 42 into the memory location, ECX, which is a register on the processor. All right, and so move ECX is B9 in hexadecimal. And the value 42 is this, 42000. It's a 32-bit word because it's a 32-bit processor, and it's in little endian order. It stores the lowest 8 bits first, and then the next 8 bits, and the next 8 bits, and the next 8 bits, which is a very strange thing to do. If you were to write it as a number, you'd write them in the opposite order, a bunch of zeros on the left and a 42 on the right. The way this is written, the significant digits are not even in order. This is the number of 16s, this is the number of 1s, this is the number of 4096s, this is the number of 256s, and so on. This little endian is a strange way to write numbers, but that's the way Intel processors work. And that is going to give us irritation through this entire course. We're going to constantly be flipping things around to get them in the right order because of this little endian thing. But anyway, this is what that instruction looks like in binary. It takes 5 bytes. The B9 will move into ECX, and the next 4 bytes are the thing to put in ECX in order. All right, so that's how it works, and that's what I say. Big endian would be the ordinary way to write something where you put the most significant number here and the least significant on the right, and then it would look like that. Little endian, you just rearrange the 4 bytes without rearranging anything inside the bytes. So you get this weird thing. All right. IP addresses, however, are sent over the network in order, not backwards. This is really important. If you take in your Net Plus, IP addresses in IP version 4, the low addresses are class A, then the next 64 class A's are class B and then class C, and this was intentional because the first couple of bits in the address determine what class it is. The first bit determines if it's class A. If the first bit is 0, the address is 127 or less, and that makes it class A. If the next bit is 0, that makes it class, and the first bit is 1, that makes it class B, and so on. So it's deliberately intended. The first couple of bits are particularly important for the earliest generation of routers back in like the 70s. That's why it was designed this way. But anyway, IP addresses are not in reverse order, they're in forward order. So it's stored in RAM this way, but sent over the network that way. So like I say, you often get confused about what order the bytes are in. All right, so the operand, you can have an immediate value like 42, and the 0x means it's in hexadecimal. That's normally you express everything in hexadecimal when you're dealing with binary code, but you could have numbers in base 10 also. Then there's registers like EAX, EBX, and ECX, and they have that name because the stuff I originally started on was the 8-bit 6402 processor, and it had one register called the accumulator, and it was called A. And that was because of mechanical adding machines from the 1800s, where you cash register, you type in a number and press chunk, and there was an accumulator that just accumulated the total of all the numbers you put in. So processors work the same way as mechanical adding machines in this respect. And then as they went to 16-bit and 32-bit, they added more registers, and to show that they were longer, they had like an extended register, and now we got extended A, extended again to get to 32-bit. Now I see a question here, 32-bit program for memory dumping, but running on a 64-bit OS, can it dump 64-bit memory? It can if it can see it. The problem with running 32-bit code on a 64-bit machine is some parts of it are reflected by the operating system. So, for example, you cannot see the whole registry on a Windows machine. You will only see the part of the registry reserved for 32-bit machines to see. So, however, I think you can dump any memory you can see. There just might be an issue of some memory being invisible to the 32-bit code. So I don't know the exact answer to your question, but that's part of it. Yep. Anyway, so here's the registers in x86, the 32-bit processor. You have EAX, EBX, ECX, and EDX. And then you've got ESP and EBP. This is the start of the current stack frame, the stack pointer, and the bottom of the stack frame, base pointer. The current stack frame goes from ESP to EBP. We're going to use them a lot. And then you have ESI, which is just used to count as you're moving an array of bytes. It doesn't really matter to us that much. And the E flags, we don't really care about either. That's where it stores the data of whether the last operation was greater than 0 or less than 0 and things like that. But EIP is super important. This is our ultimate goal. You are trying to gain control of the EIP. EIP is the instruction pointer. That is the address of the next command to be executed. And if you can control it, you control the box. That is your goal. You want to get control of EIP and move it to a command other than what the developer intended, and now you're in charge of the box. So that's what we're going to do. And the normal way we're going to take over EIP is with a Stack Overflow, and that's going to involve understanding ESP and EBP. So these are the main registers we're going to focus on, ESP, EBP, and EIP, in doing Stack Overflow attacks, which is mostly what we're going to do. After you learn how a basic Stack Overflow works, all the other attacks are variations on that. All right, so the general registers are used by the CPU like EAX and EBX just to store any temporary value. There's segment registers we don't have to worry about much, and status flags. The instruction pointer, as I mentioned, is really important to us. That controls which instruction will be executed next. All the ones are 32 bits in size. You can refer to smaller pieces of a register if you want to. You can reference it 8 bits. AL is the lowest 8 bits in the 32-bit EAX register. And the reason you have the ability to refer to 8 bits is so you can run old code. You can run 16-bit code on a 32-bit processor, and you can refer to just 8 or 16 bits. And this will turn out to be important to us later just to improve our exploits. And here's how it looks. The EAX is 32 bits wide. AX is the lower 16 bits, and AL is the lower 8 bits of that. So you can refer to 8, 16, or 32-bit sections of a register. Normally, all commercial and modern code will just always use 32-bit references, but hackers typically use these ones here in order to avoid having null bytes in your construction. I just mentioned back here, this command here, yes, it could be an address or data. But if we go back to this one, this command to put 42 in ECX, this is what it looks like in binary. It has 3 bytes full of 0. This is really bad because nulls normally terminate a string. So if you're trying to inject a series of commands in a text field, this will terminate it early. So what you want is to write code which does not include any null bytes. And that's why you would not use the 32-bit version of this number. You would use the 8-bit version of this number that wouldn't have all those zeros. That's why this little rather obscure process here, which a normal programmer would never worry about, turns out to be very important to hackers to understand how to do that. All right, and so, all right, your general registers can normally be used interchangeably, but there are a few instructions that use specific registers. There is multiplication and division in modern processors. When I started, those things did not exist. You had to write your own code to do it, and they use these special registers for that. But we don't need to do any multiplication or division for anything normally here. That's only used for things like 3D rotation in games and stuff like that. Compilers have conventions of how they operate, and GCC and other compilers typically use EAX for the return value from a function call. So you call something like printf, and then you get a return value in EAX, which is like 0 if it worked and 1 if there was an error. And that's what you'll find coming back every time you return from a function, typically. Then the status register, yeah.
Is that like all compilers that will return?
No, not necessarily. No, it's just all the common ones. I bet there are exceptions, although I don't know any right offhand. But there are a bunch. It's just a decision made by compilers. It's not enforced by the hardware at all. The hardware doesn't care what you put in the registers.
They just use it as like an industry standard or?
Yes, yeah. Exactly. And so there are flags in the status register, and they have things like whether the last result was 0, whether you added numbers and they overflowed the number of available bits and there's an extra bit to be carried and so on. And that's what it uses in the hardware to do things like jump less than 0, jump equal. Normally you don't look directly at status register yourself. You just use assembly language commands that will jump on a condition, and this is what it's using to run the condition. So you don't normally have to look at this directly. Now I see a question here. I was reading about ROP chains. Yes, we're going to do ROP chains. The video did not account for the null bytes. I'm confused about how it works. Yeah, ROP chains are very nice. In a ROP chain, you have, say, a modern operating system. You're injecting code into a data field, but you cannot execute any of that data because that memory section is not executable. So what you do is you put in addresses, and the addresses point to code that was already there, code the developer put there. And you have a series of addresses, and that's your exploit. And the address, you jump to some code that was already there and execute it, and hit it return. It comes back and executes the next one and the next one and the next one. So by a series of nothing but addresses, you can write code by patching together pieces of code that were already there. That's what a ROP chain is, return-oriented programming. We're going to do it, you'll see. Null bytes have the same problem in your ROP chain. If you're injecting a ROP chain into a text field, if any of those addresses contain a null byte, they'll break your string. So you have to find addresses that contain the instructions you want and that don't move or reliably and that don't contain any null bytes. We'll do all these things, but it turns out to be a little tricky to find appropriate addresses to use for ROP chains. That's a good question. There are 32 possible flags. No, there aren't. I think there's only like 8 flags. So I think this register, I don't think there's that many of them. 32 bits in size, but I don't think there are 32 bits. I only know like 4 of them. But I haven't paid a lot of attention. It's a good question, and you'd have to find out by reading the Intel reference manual. All right, the EIP is the main target we want. This controls the address of the next instruction to be executed. And so if you control this, you can take over the machine. If you just corrupt it with wrong data like AAA, then it will just crash on an invalid address because the address AAA is probably not allocated for use by your program. And so that's why normally you just inject code, and when you see a crash, that's why a sloppy fuzz will cause a crash. You manage to gain control of the EIP, but you put random junk in it, so it crashes. Then a more careful exploit will carefully write a valid address into EIP, which will do something more controlled than a crash. All right, so let's try another Kahoot, which would be this one. Here we are, 1B. All right, and it looks like we're coming up on the hour, so we'll take a break after this. Yeah. Let me take a look and see what's going on. You can change it dynamically. Oh, that's good. So you can react to things. Well, that looks like fun. All right, good. All right. maybe we got as many people as are coming. Wait a few more seconds. We're up to 14. All right, let's give it a shot. So, all right, so what kind of language is most malware written in? It's mostly 32-bit code because 32-bit code will run on 64-bit machines. So that's a general way. Although these days, more and more malware is changing to 64-bit code because 32-bit machines are not so common anymore. All right. All right, so that's the loopback address. What kind of notation is that? That is big endian, in the normal order a mathematician would write it. The big numbers on the left and the small numbers on the right. It'll be stored the other way on an Intel processor. But this is written in big endian, the most significant digits on the left. And this 7F is 127, so this is the address 127.0.0.1. All right, so what is move and an XOR? What are they? Okay, those are mnemonics. That's the start of it, that's like the verb. They call that a mnemonic, which is the type of operation that's being performed. All right, instruction places data into EAX. So what type of operand is EAX? It's a register. EAX, EBX, ESI, all these things are registers. They're little memory regions on the processor itself. All right, so you put data into bracket EAX. What kind of operand is that? Yeah, that's a memory address. We didn't mention it. When you put brackets around it, it means take the value in there and interpret it as an address and go into main memory to that address. The square brackets mean indirect addressing. This is a pointer to the location. So if you move into bracket EAX, you'll take EAX as an address and write into main memory at that address. All right. Sig, all right? Zaza will have to tell me who they are if they want their points, unless that's a real name, which I doubt. And Root, I know who that is. All right. I think it is, yeah, it's just about 7. So let's take a break until 7:15. Then we'll do a little more of this. I certainly don't intend to lecture for 3 hours. I never do that, but we usually do about an hour and a half and then just answer questions. So go ahead and take a 10-minute break. And then we'll pick up. I'm going to turn off the recording.